Hello students, now in this video let us solve some more examples on congruences. So example, show that 39 divides 53 raised to 103 plus 103 raised to 53. This thing we have to show. So now if we show this addition congruence to 0 modulo 39, then also we can say 39 divides this one. Remainder should be 0. So let us find first this term 53 raised to 103 congruence to what modulo 39. This term we will find separately, and 103 raised to 53 congruence to what modulo 39. While finding these two separately, simply we have to add them. These are get added and that value should be 0, then we get this one. Fine. Now let us find out them separately. So let me start solution. We can say here 53 and 39 are what? Relatively prime. They are relatively prime. Therefore, by Euler's theorem, what can we say? 53 raised to 5 of 39. 53 raised to 5 of 39 congruence to 1 modulo 39, as they are relatively prime. This is our Euler's theorem. Fine. This one, let me write again. This is 5 and here base is 53. Now 5 of 39, let us find out that term first. What is 5 of 39? 5 of 39. Now 5 of 39 can be written as 5 of 3 into 13. So that will be 5 of 3 into 5 of 13. We can write it as, this is one of the property of 5 function. Now 3 is a prime number. If p is a prime, then phi of p is what? P minus 1. So using that property, 3 is a prime, 13 is also prime. So here phi of 3 is 2 and phi of 13 will be what? 12. So phi of 39 is 24. So we get the value of phi of 39. So let us substitute that value here. While substituting, therefore we get 53 raised to 24 congruence to what? 1 modulo 39. Now we need 53 raised to 103. So let us divide 103 by 24. Let us check what happens. As 103 can be written as 24 into 4 plus what? 7. Plus 7. So if I take fourth power here of this equation, still remainder will be what? 1. Or let me take this 53 raised to 103 can be written as 53 raised to 24 into 4 plus 7. That is 53 raised to 24 raised to 4 into 53 raised to what? 7 modulo 39. Let us write it as such. Now this is, we know this one modulo 39 is how much? 1. So this is 1 raised to 4 into 53 raised to 7 modulo 39. Now this is congruence to, this is equivalent to what? This is equivalent to 53 raised to 7. Now let us check what is 53 modulo 39. This base 53 modulo 39 is 14. So it will be 14 raised to what? 7 modulo 39. Why? Since 53 congruence to 14 modulo 39. This one, the reason for this step. Okay. Now after this what we get? After this, here this 53 raised to 103, what does it give? Here onwards, let us solve here onwards. This 7 can be written as 14 raised to 6 plus 1. For our simplification, so that the calculation becomes easiest, we will do that. So 6 can be written as such into 14. This is how much? 7 modulo 39. Okay. Now here, this is 14 square is how much? 196. Its cube into 14 modulo 39. So this is equivalent to 1 cube into 14 modulo 39. Now here again a reason, 196 congruence to what? 1 modulo 39. Why does this? We can find it 196 equal to 39 into what? 5 plus 1. So quotient will be 5, remainder is 1. So that's why this is a step. Okay. So here what we get? 1 cube means 1 and 14 is here. Means we get 14 modulo 39. So finally we get 53 raised to 103 congruence to what? 14 modulo 39. This is our equation number 1, suppose. Now let us do the work for 103 raised to 53. Now this 14 is less than 39, so here onwards we can't do anything. Here we have to stop. Now we will work on this part here. Again, what can we say? 39 and 103 are also what? Relatively prime. Again we can apply Euler's theorem. So by Euler's theorem, what can we say? 103 raised to 5 of 39 congruence to what? 1 modulo 39. This is the step again. Again 5 of 39 is how much? 24 already we have found. So we can say 103 raised to 24 congruence to what? 1 modulo 39. Okay. What is the reason? Since 5 of 39 is what? 24. Okay. This is the reason here. This is the reason. Okay. Now we need 53. So what is here? As we can say, as 53 is equal to 24 into 2 plus what? 5. Therefore this 103 raised to 53 can be written as 103 raised to 24 into 2 plus 5 modulo 39. So that is what? 103 raised to 24 its square into 103 raised to what? 5 modulo 39. Okay. So now this part is 1. So 1 square, this is congruence, sorry. 1 square into 103 raised to 5 modulo 39. So now 103 congruence to minus 14 modulo 39. So here this is congruence to, this is 1, this is 103 raised to 5. So this is minus 14 raised to 5 modulo 39. Why does this? Since 103 congruence to minus 14 modulo 39. This is a reason behind it. Okay, fine. Now simplify this one. Let us simplify it. What does that? The simplification for that will be, let us simplify it. Now this minus 14 raised to 5 odd number is there. So after all it will be negative. So let me take negative sign outside. So here this is 103 raised to 53. Congruence to minus I will take outside. I will write 14 square, its square into 14 modulo 39. We can write 5 as it is, 4 plus 1. Now this is minus, this 14 square is again 196, its square into 14 modulo 39. Okay, this is equivalent to 196 congruence to what? 1. So minus, here it will be minus what? 1 square into 14 modulo 39. Okay, so this is how much? 1, and this is, so it will be minus 14 modulo 39. So what we get? 103 raised to 53 congruence to minus 14 modulo 39. This is our equation number 2 suppose. Our equation 1 is for this 53 raised to 103. It congruence to 14 modulo 39, and 103 raised to 53 congruence to minus 14 modulo 39. Now let us add equation 1 and 2 by 1 plus 2. What we get? This is 53 raised to 103 plus 103 raised to 53 congruence to what? 14 plus minus 14 modulo 39. Modulo 39. That is what? 0 modulo 39. And the same we want, this remainder of this addition should be 0. Then we can say 39 divides this addition. Therefore, we can say 39 divides 53 raised to 103 plus 103 raised to 53. This is our answer here. This is the required part. Okay. Now let's take the next example. Next one. If P and Q are distinct prime, and if A raised to Q congruence to A modulo P and A raised to P congruence to A modulo Q, then show that A raised to PQ congruence to A modulo PQ. Okay. Solution. What is given to us? Given that what this A raised to Q congruence to A modulo P, A raised to P congruence to A modulo Q. A raised to Q congruence to A modulo P and A raised to P congruence to A modulo Q. This is given to us. This is Q. Okay. This part given. What is the claim? We have to show A raised to PQ congruence to A modulo PQ. That part we have to show. So now as P and Q are prime, are what? Prime. So by Fermat's theorem, using Fermat's theorem, what can we say? We can say A raised to P congruence to A modulo P and a raised to q congruence to a modulo q. Okay, now this gives us, what does this say? This says a raised to pq congruence to a raised to q, taking qth power on both sides here, modulo p. Okay, and that is equivalent to a modulo p. Why does this? Because a raised to q congruence to a modulo p from given, and again a raised to pq congruence to, here applying p on both sides, taking pth power on both sides, a raised to p modulo q, and that is again congruence to a modulo q. This is what the reason from given. Okay, this is the reason for that. Now a raised to pq congruence to a modulo p, a raised to pq congruence to a modulo q. So what does this say? P divides a raised to pq minus a, and q also divides a raised to pq minus a. Now same term is divisible by p as well as by q. So we can say their product also divides a raised to pq minus a. Why does this? Since p and q are distinct primes, so they are what? Relatively prime. This is the reason for that. So choosing this one, what can we say? A raised to pq congruence to what? A modulo pq, and that is our requirement. Okay, now let's take the next example. Next example is that find the remainder, 15 factorial when divided by 17. So let us start solution. Now factorial terms, so let us use Wilson theorem. What the Wilson theorem says? By Wilson's theorem, we know p minus 1 factorial congruence to minus 1 modulo p. Now our p is here 17. Here p is equal to what? 17. Therefore, using this one we get 16 factorial congruence to minus 1 modulo 17. Okay. So now 16 factorial can be written as 15 factorial into 16 congruence to minus 1 modulo 17. But 16 itself, 16 the number itself congruence to what? Modulo 17 minus 1. So I can write here 15 factorial into minus 1 congruence to minus 1 modulo 17. Since 16 congruence to minus 1 modulo 17. So here on both sides this term minus 1 is there, so this negative will get cancelled. So what can we say? 15 factorial congruence to what? 1 modulo 17. So the remainder of 15 factorial when divided by 17 is how much? 1. So we can say here the remainder of 15 factorial when divided by 17 is 1. This is 1. Now the next one, the next example is find the last digit, find the last digit in expansion of 2 raised to 400. Now solution, already we have solved such a kind of question. Now last digit means unit digit we have to find, so we will take modulo 10. If last 2 digit, then we will take modulo 100. If last 3 digit, we will take modulo 1000. As such, already I had explained previously. So now let us start with modulo 10. So 2 raised to 400 can be written as 2 raised to 5 raised to 80. Why does this? Because 2 raised to 5 is 32. 32 raised to 80. Or 2 raised to this 5 into 80 will be 400. So 2 raised to 5 will be 32. Using that we will simplify it. Modulo 10. Now this can be written as 2 raised to 80 modulo 10. Why does this? Because look at here now. Since reason 2 raised to 5, that is how much? 32, and that is 2, that is congruence to a 2 modulo 10. This is the reason for this step. That's why 2 raised to 5 can be written as 2 raised to, it will be 80. Again this is 2 raised to 5 raised to 16 modulo 10. Again this 2 raised to 5 will be what? 2. So 2 raised to 16 modulo 10. Now this is again 2 raised to 5 cube into 2 modulo 10. So 2 raised to 5 is again 2 cube. So 2 cube into 2 modulo 10. So 2 cube is 8 to 0, so that will be 16. 16 modulo 10. And 16 modulo 10 is how much? 6 modulo 10. So what will be the answer? The last digit in expansion of 2 raised to 400 is what? 6. This is 6. Now here we will stop for this video. Next video we will see some more examples. Thank you.